Okay, sorry. Welcome back to hydrogeology lecture on evapotranspiration, GEO420 at the University of Montana. I had to leave for a master's thesis defense, and if you went and saw it, it was all or a lot on this exact topic we're about to talk about right here. So we're talking about radiation balance and evapotranspiration at the surface. And R here is the, it's actually the net radiation. All right, so this is incoming shortwave radiation from the sun, all right, which is this white stuff, minus the long wave radiation that is emitted and minus anything that gets reflected. So this is the net radiation. All right, and that's this incoming minus the long wave going out. All right, and this, I'm going to put an N on there to signify that it's net radiation, which is this incoming minus the outgoing. So the net radiation, all right, which is essentially the net radiative energy supplied to the surface, goes into heating the ground and converting, and that ground then heating the air, all right, or converting water into gas. So we can write this as the heat flux, the sensible heat flux at the ground, and that's essentially heat being transferred from the ground into the air and heating the air. So sensible heat flux plus the latent heat, that's this lambda, times the evaporative flux. And then that's also equal to, we've got some amount of deep geothermal heat coming in here. So we got some geothermal heat flux too. We call that the ground heat flux. All right, so H, so Rn is the net radiation. H is the sensible heat flux, H with a bar over it. And my note-taking software is horrible again. Sensible heat flux. Essentially, the heating of the air into temperature that you can measure. Lambda is the latent heat. Latent heat is the amount of energy it takes to vaporize the water. So we call that the latent heat of vaporization. And E is the evaporative flux. This is the water leaving via evapotranspiration. So this is the ET flux. ET water flux. And then G is the geothermal heat flux or soil ground heat flux. All right, so um, okay, so we can rearrange this equation because we can measure things like the net radiation. We can measure the air temperature and the ground temperature, and we can calculate the sensible heat flux, and we can measure the geothermal heat flux, and we can isolate the evapotranspiration, right? And so there's a whole suite of methods that use this radiation balance to solve for the evaporative or the evapotranspirative heat or water flux. And there's a litany of these, and some of the more common ones that I want you to at least have heard in my class are the Penman or the Penman-Monteith methods. We're not going to get into those equations because we don't have time, and because you can take hydrology from Marco Mineta in geosciences, where they really, Marco's is going to spend a lot of time on this, and this is a big part of surface hydrology. And so I just want you to know that radiation balance is a really important way that we can calculate ET, and that one of the ways that we're going to look at is by recognizing that the radiative balance, we could say probably, the more net radiation we have, the higher the air temperature is going to be. All right. And so it makes sense that the higher the air temperature, the more water we're losing to evapotranspiration. So in a loose way, in an empirical way, what we're going to talk about, the Thornthwaite equation, allows us to estimate potential evapotranspiration just using the air temperature. All right, so it's essentially isolating the sensible heat flux and saying the hotter the air temperature is, the more evapotranspiration we're going to get. There's lots of these radiation balance methods. And in fact, if you want to get the best sort of distributed measurements of ET available right now, sort of the analogy of GridMet or PRISM for ET, they're going to be based on these radiation balances because satellites can see incoming and outgoing radiation from the Earth. And if we make some assumptions, we can then estimate ET. So just so you have some of their names, the Penman and the Penman-Monteith. And these are essentially empirical relationships that relate sort of semi-empirical relationships that relate the radiation balance to the evapotranspirative flux using this radiation balance equation. All right, so another empirical method that we're going to use that requires only knowledge of temperature is the Thornthwaite, and it's sort of loosely based. Thornthwaite method, and it's loosely based on the radiation balance, in that it's using just the temperature. but it's a sort of fundamental way to calculate or estimate potential evapotranspiration using temperature only. And the Thornthwaite equation goes like this: the PET, all right, for a month, all right, is given by 1.62 10 to the TAI over I times A. All right, and this PET is the average PET for a month, I, in units, centimeters per month. All right. TAI is the average temperature for that month. All right. And I is the heat index. And it is calculated using this equation, sum I equals 1 to 12 TAI I think that's 5. My notes are terrible. It's on your homework though. To the 1.5. All right. And then finally, A is equal to 0.492 plus 0.0179 times I minus 0.0000771 I squared plus 0.000000675 I cubed. All right, anytime you see this kind of equation where you got something that's raised to the first, second, third power, and the plus and minus alternates, it's an empirical equation. That means it's just based upon a bunch of data, and they figured out how to relate, say, PET to the average temperature using this empirical formula. All right, some caveats here. If the average air temperature is less than 0, we're just going to assume it doesn't contribute to the heat index. Actually, and so this should become 0. And also the PET for months where the average temperature is below 0, we're just going to assume it's equal to 0. So when your average temperature is below 0 here, you just say, hey, PET is equal to 0. Otherwise, you get a negative number here and you get this negative PET, and it doesn't make any sense. So we're basically only going to do this for so TAI greater than 0. Okay. So this Thornthwaite method basically allows us to estimate potential evapotranspiration. All right, remember, evapotranspiration is if we had all the moisture in the world um, given the air temperature. All right, and it's a crude estimate. It doesn't include other things that affect evapotranspiration, and we can go way down the road. Calculation of evapotranspiration, you could spend a whole class on, honestly. I mean, sorry, a whole semester on. But this is a way to do it, and it's a way that it can be done with a data set that's commonly available. All right, there are methods that use the distributive or use the radiation balance and get at distributed evapotranspiration, and I'm just gonna point you to one right now, and this isn't necessarily the best one, but it is one that is out there, and so this is the actual evapotranspiration modeling using the operational simplified surface energy balance approach. All right, so this is produced by the USGS. All right, and it's a method where they estimate AET, actual evapotranspiration. They're using that surface energy balance, all right? And then they modify it using satellite imagery of greenness. So they're looking at how green the plants are. And that gives them some idea of how much ET there is. I just want you to look at a few things. So this is seasonal mean actual evapotranspiration for the year 2000 in millimeters, and they've done it at a county scale. And you can see, some regional patterns. So here, for example, in Nevada, you see very low actual evapotranspiration. And that is due to exactly what we discussed before. This is a big desert. There isn't much water around. If you look at the satellites, there's no greenness, all right? And so you don't get a lot of ET. Similarly, in the Utah deserts, all right? Eastern Montana, less ET, all right? It's a lot less green versus Western Montana, all right? Even though we get more moisture in Western Montana than Eastern Montana, we have less ET or greater ET. Yeah, and I was gonna see if we just had a, so at any rate, this is one of many products. Some caveats on these ETs, they are usually based on measured evapotranspirations from a reference crop, which is usually alfalfa. And so, they're like a crude estimate. And the bottom line is ET is really hard to measure, and it's even harder to estimate, especially actual evapotranspiration. So the Thornthwaite method is at least a method that we can use. It's published and it's defensible, and it would be a way that you could say, hey, if I wanted to calculate the minimum recharge, then I could look at precipitation minus PET, and I would know that, I am maximizing the potential evapotranspiration. And so then I'm putting a constraint on the minimum recharge. All right, the final thing that I wanted to get to was how we can measure actual AET, sorry. And there's a method that allows us to do it. And then I just want to look at the difference between AET and PET. Okay, so if we wanted to measure AET, again, it's really hard, but there is one method that we can use, and it's let's think about this grassy surface here. So here's the land surface, and then let's imagine that we sort of cut that surface, and we essentially bury a barrel that has all of our veg and our soil. All right, so and beneath us here is the soil. All right. Here's the edge of our line. So we got soil here, and we got this bucket. All right. And it's full of soil, and it's got all the roots and everything of the grass. And it just sits in the grass like a normal bit of soil, but we can weigh this bucket, so we could put it on a scale, right? So the bucket's sitting here on a scale that's measuring how heavy it is. All right. And so we rain, we get precipitation, we fill the bucket up a bit, and then we calculate, and then we have ET loss. And as we lose water to ET, the bucket will weigh less and less. All right. So this is called a lysimeter. All right. And it essentially measures AET. All right. And we can do it by weight. We could also, there's other ways we can measure it, but the weighing lysimeter, where we just weigh the bucket, is probably the most accurate. All right, these are great, but you could imagine that they work fine for grass. All right, but you couldn't install these, say, in a forest, because you couldn't put a tree on them. And there are actually a couple huge lysimeters that now have big trees in them, but there's just like one or two in the world. And they're on flat ground, they're not on hill slopes. So this is, a way to measure AET, but it's limited. And then there's another way. And again, this is just so you sort of have been introduced to it enough that if you were interested in actually calculating or measuring ET, you know some of the methods. And in this method, let's say here I have a sort of grassy surface with some trees. All right. And the wind is blowing across my surface. All right. And as it sort of hits trees and stuff, the wind loops and it's turbulent flow. All right. And the water vapor that's coming up off of my land surface gets entrained in this, and it's sort of carried along. And we can use what's called a flux tower. And the flux tower sort of looks at, it's got two sensors of water vapor. and sensors of air velocity. And it sort of looks at the covariance of velocity and water vapor. All right. And it's basically just measuring water vapor concentration and air velocity, and then backs out AET. All right. And it does it over this sort of whole swath of area that's upstream of the flux tower. So this is called an eddy covariance flux tower. All right, and it measures AET using wind speed and water vapor concentration, and at two heights, and they need to be pretty high. They need to be sort of at the level of the vegetation. And there's a whole lot that goes into this, and these things are hard to install, and the data analysis to turn it into ET is impressive, but I want you to know what they are. They are these towers, and they look at wind speed and water vapor concentration, and they get AET. All right. Okay. So finally, I wanted to just end our conversation by coming back to recharge, and think about recharge, and when it occurs, so I want to just make a plot here. I'm going to make a plot here. So let's go AET, PET, P, and R. And I just want to sort of think about what these variables look like seasonally in a place like Montana. So we'll start here and do this monthly. So January, February, March, April, May, June, July, August, September, November, October, December. Do a little erasing here. March, April, May, June, July, August, September, October, November, December. So here's a year. All right, so precip in Montana. Well, let's call this precip plus snowmelt. All right. So January and February, and I'll make precip be and snowmelt be white. All right. So January, February, we're getting precip. All right. At a pretty steady rate, roughly. All right. And then and that goes through March, and actually April is our wettest month in Montana by a little bit. All right. But starting in April and May, snow melt really kicks in. All right. So we get this big increase, and then precip and snow melt go away, and then start to come back up in December. All right. So our driest months are sort of July, August, September, and October in Montana. All right, and then let's think about what what PET does. And PET is probably, we're going to go with red here. All right, so PET, during these months is low, during the winter is low. And then and then it starts to pick up in spring, all right? And then in summer it gets really high, all right? And it continues up really high and then comes back down here in the winter, all right? Well, it should come down faster. All right, in the winter. Okay, so let's think about what AET would do. All right, so AET would be low here and be equal to PET here, and then it would probably even increase. It would increase here. I'm not moisture limited, so it would increase along with the AET until conditions started to get much drier, and then you would see that the AET would come back down. All right, and basically during this period, it should come right back down pretty close to the value of precipitation, and you're losing almost all your water to ET, but the PET is basically just equal to precip. Okay, so let's think about what happens. So I should write these. So this is so R is PET, or red is PET, green is AET. And then finally, let's think about what is recharge. So recharge can occur when my precip plus my snowmelt is greater than AET and PET. And even though so we know it has to be at these points where precip plus snowmelt are greater than AET. But the problem is that during January and February and even into March, even though we're getting precip, it's all as snow and it's sort of locked up. So nothing's entering the system. So recharge is low here just because everything's frozen, all right? But as soon as snow starts to melt, all right, here in March, recharge is gonna increase, all right? And it's essentially gonna be equal to the P minus the AET, all right? And I'm gonna kind of try to make that plot here. And as these two start to coincide, all right, it's gonna come back down. And as soon as they equal each other, the recharge is gonna be equal to 0. So this zone here from about April, really probably mostly through June, in most cases, but here the way I've drawn it through July and August even, is the time where we might see recharge to the groundwater system. But for the rest of the year, all precip, it essentially gets lost to ET or is locked up in the snowpack. So this is really our recharge period. All right, and for a lot of the year, PET is greater than precip, and during that time, AET is basically just equal to our precip. All right, and during that time, there's no recharge. Okay, so that's my discussion of evapotranspiration. Again, this is a huge topic. Take Marco's class to really get into it, and I would recommend that highly. But for us, this will be good enough. All right, I'll talk to you guys later. I'll see you in class, and have a good day.